Hello, everyone. Today we start to discuss about the work and energy. That is chapter 4. And the PowerPoint is already on your D2L. And we can just go and see what all we need to discuss. Like, if you remember, whatever we discussed in the previous chapter, like regarding force, similar things we are discussing over here. Now, the only formulas that we'll be using formulas related to work and formulas related to energy. Now, if you look at this thing here, the only formula we need right now is the third one. The third one says work is force times distance. Whenever you look at, whenever they discuss what is work done is a force times whatever is the distance traveled. That is the work. So if you read the definition at the beginning, it says the product of the magnitude of the force and the parallel distance through which the object moves is called work. So if there is an object, let's say this is an object, and this object is moved about, say, 5 meters, 5 meters. And let's say a force of 10 newtons, is required to move this object. Force of 10 newtons is required to move the object from one place, place A to place B. A force of 10 newtons is required to move an object from place A to place B. That is what, 5 meters apart. So I will say this is force. This is the distance or displacement. So your work done will be 10 times 5. That is what? 50. And what are the units? Units are Newton meter. Units are Newton meter. Now we'll come to this point. If we look at this over here, this shows, now over here, what a person is trying to do. The person is trying to push a wall. Now he's applying force on the wall, but the wall is not moving. If the wall is not moving, that means this D is what? 0, and 0 times F will give you 0. If the wall is not moving, we will say that the work done is 0. There is no work done at all in this place. So the work done is 0 in this case. Okay, now this is the case that I discussed earlier. The product or the object was at this position. This object is displaced or moved through the distance D. And what moved this box? What moved this box? This box is moved by the force F. So what is the work done? Work done is F times D. Now, if there is no displacement or if there is no change in position, I will say that the work done is 0. No work done actually. But right now, the product is moving. The object is moving. The object moved from one place to another. How much distance it moved? It moved D distance. It moved D distance. And what made it move? The force F made it move. So whenever I say work, work is force time distance. We just need to remember, we multiply force and distance to get work. Okay, now another thing. When we are using a lawn mower, what happens? Now, the thing is, the force is F, and that F has two components. One component is a vertical component, another component is a horizontal component. Every time, now onwards, we'll just differentiate force into two components. One is vertical, other one is horizontal. Like, if I am moving one thing from here to here, this is horizontal, all right? If we have, say, something at this position, and I need to rise it up to this position, that is a vertical component. But right now, when we are moving a lawn mower, there is, well, I'm not moving it vertically or horizontally. We just push it. We just push it. Now, pushing a lawn mower will result in two forces. One is the horizontal force, and the other one is the vertical force. Now, right now, Since this lawn mower moves in the direction, in a horizontal direction, we will just use the horizontal component, and that will give us force times distance will be work. We are not using this vertical component. We are just using the horizontal component of the force. So now when we reach to those questions, we'll understand what is the difference between horizontal component and the vertical component, all right? Till that time, you all should know that there are two components, horizontal and vertical. So we'll see which one we are using or which one we are actually, which one we need. We just need to see which component results in motion. Now over here, now you know one thing, this lawn mower, it will not move up or down. It will not move up or down. It will just go right or it will go left. So right and left, which component is moving right or left? The horizontal component is moving right or left. Okay, now, so in this case, we are not using the vertical component. We use the horizontal component of force. Fh times d gives us the work done. All right, now in the SI system, very important. Please make a note, click a picture or whatever. This is very important. Now I said work done is force times distance. Force is calculated in newtons, distance is calculated in meters, and the unit of work is Newton meter. Unit of work is Newton meter. Now this Newton meter is actually called joule, Joule, and is represented by J. Whenever you see J, J means what? J means Newton meters. Newton times meter. In the British system, they are using it as a pound times foot or foot times pound, but most of the questions will be having Newton meters. All right. Now, just a recap. I said force. Force was mass times acceleration. Mass was kilogram, acceleration was meters per second square. That is force. Now this is work done. Work done is force times distance. That is what force. The units of force are these. Now this unit is actually Newton. Unit of force are Newton times meter. And what is Newton? If I plug in the value for Newton, Newton is kilogram meter per second square times meter. All right, that is actually what? Kilogram meter square divided by second square. Or we call this unit as joule, Joule, joule. That is the SI system for your what you call it, work done. That is joule. Okay. Now here are a few things that we need to note. First thing is, when work is done, we generally feel the other part of Newton's third law acting against us. Now, when the work is done, let's discuss the example. If we are moving something from one place to another place, Newton's third law says what? There is an equal and opposite reaction. When you move this thing in this direction, there is a friction force that will move it backwards. All right, and that is a Newton's third law. Gravity and friction are common agents working against work. Friction, your car is moving, something is stopping your car. What is that something? Friction with the road, friction in the engine, friction in the air. All right, you are writing with a pen, your pen stops actually when you write it. There is a friction between your pen and the paper. All right, now when the gravitation, if we look at the launch of a spaceship, the gravitation will pull it backwards. Airplanes, the gravitation will pull them downwards. So these are the things that work against work, that are working against work. In case of gravity, we must apply force to overcome the force of gravity. So the weight mg, we have to overcome this thing. So work is what? Work is force times distance. That is, in this case, force is the weight and distance is the height. So whenever it is like this, whenever the work is done upwards and downwards against gravity, we call the work as simply mgh. Now I'll explain why we call it mgh. The reason we call it mgh is we have work as force times distance. Now force is weight. Weight is mg, and distance is the height. Height is h. So we call it mgh. Weight times height. So whenever anything is lifted upwards, like you lift something from the ground upwards about say 5 meters up, using a crane or using a pulley or using something, then that is called the work done. So what you actually multiply in that case, you multiply the weight of the body times the distance it is moving, height. mgh is the work done. This is the horizontal work done. Okay, now energy is the ability to do work. There is no different unit for energy. It is the same, quite similar to one that we have been using earlier. So when we look at this energy, energy is quite similar to what we say is work. So energy is, the definition says ability to do work. An object or a system that possesses energy has the ability to do work. When work is done by the system, the amount of energy of the system decreases. Now okay, now when we look at this, when a work is done by a system, let's talk about your car, the amount of energy in the system decreases. How does the amount of energy decreases? Energy decreases in form of a fuel. If you keep doing work, energy decreases, you feel fatigue, you need something to eat or drink if you keep doing work. Okay, so when you keep doing work, the body needs more energy. The energy of the system decreases. When work is done on a system, the system gains energy. When work is done on a system gains energy. System, well, there are two different things. On a system, previous was by the system. All right. If you are doing work on some system, the energy of that system will increase. The work is a process by which energy is transformed from one object to another. Work and energy have the same units. They have the same units, that is joule. So if we ask work or if we ask energy, they actually have the same units. Now, here we are discussing two energies. Let me see. Yes, over here we are just discussing two energies with you all. The first one is a kinetic energy and second one is potential energy. So number one, kinetic. As the name says, it is associated with motion. Kinetic energy. The energy of the object, the energy an object possesses because of its motion is called energy of motion, or we call it kinetic energy. Very important formula. Whenever you see this thing written, this thing means what? EK means it is kinetic energy. This K stands for kinetic. And what is EK? EK is 1/2 mv square, where m is a mass, that is a mass, and v is the velocity of the object, mv square. Okay, now this is your kinetic energy. This is the formula for kinetic energy of any system. Now they say if the object is already moving, how do we calculate kinetic energy? We calculate kinetic energy for final speed, kinetic energy for the initial speed. Like they just mean to say if the car is moving, all right? If the car is moving and we try to find what is the change in kinetic energy. What is it over here? Mass remains the same for both the times. Mass will not change. The only thing that will change, initially the velocity was v1 and now the velocity is v2. So we calculate the formula for kinetic energy at the second place is 1/2 m v2 square. Over here it will be 1/2 m v1 square, and we subtract both the energies and we get the difference of energies. We get the work done, or we get the kinetic energy or change in kinetic energy. We call it change in kinetic energy. Like they may ask you, a car is moving at, okay, let me draft one example. There is a car, or there is an object, say weight of the object is 1 kilogram. It is moving at the velocity of 7 kilometers per hour or 7 meters per second. Okay, and later on, we apply some force. The object is same, but now it is moving at the velocity of 10 meters per second. What is the work done? Work done is, I will calculate energy over here. How? 1/2 mass times velocity squared, 10 squared. And over here it will be 1/2 mass times 7 squared. 10 squared is 100. It is 100 divided by 2, that is 50 joules. And this is 49 divided by 2, that will be 24.5. So your answer will be 50 minus 24.5. That will be actually 25.5 joules. That is the work done in moving an object, or when an object is moving at 7 meters per second, but now the object is moving at 10 meters per second. The work done to increase the speed. The work done to increase the speed, and that is what we have. So what I did, I calculated the final kinetic energy, and then I calculated the initial kinetic energy and subtract from that. Okay, now this is what we have to do in kinetic energy. Like they have another example. If 1 kilogram ball is fired from a cannon, what is the change in the ball's kinetic energy when it accelerates from, see, initial velocity was 4, final velocity is 8. So I calculated both the kinetic energy. First, I calculated the final with the 8 meters per second. So the formula for kinetic energy is half m v square. For the second one, half m v square. But the only thing you have to make sure is, the only thing you have to check is, initially the velocity was 4 here, and the final velocity is what? 8. And when you simplify, 8 squared is 64. 64 times 1 is 64, and divided by 2 gives you 32. 4 times 4 is 16. 16 divided by 2 gives you 8, and 32 minus 8 gives you 24 joules. All right, now these questions are important. You can see these questions on your exam for sure. You'll see similar questions on your exam. Okay, now auto braking. Work to stop auto, or braking force times the distance. Now, when we apply brakes to our car, again, the car do some work. What is that for? That work is actually braking force times distance. Now, if you're solving question, they will actually mention what is the braking force. They'll give you the braking force. Now, Work is kinetic energy, that is half of mv square. Now half of mv square will actually be equals to F times d. So if the velocity of a vehicle is doubled, the braking distance becomes 4 times. Very important. Very important. If the velocity is doubled, the braking distance actually increases 4 times. And if the velocity is tripled, the braking distance is increased 9 times. This is the reason, like if I say if I'm moving at the speed of say 20 miles per hour, and if I am moving, if I, okay, let's say 20 miles per hour, and my car stops in 5 meters. And if I increase the speed, if I double the speed, double is means 40 miles per hour, double. Now what they say about the distance become 4 times. It was 5 meters earlier, now it will be 4 times 5, 20 meters. If I triple the speed, triple means 3 times, 60 miles per hour. Braking distance will be what? 5 times 9, 45 meters. It increases a lot. The braking distance increases a lot with the speed. Braking distance is how much time will your car take to stop. So it is actually application of velocity or application of work. All right, next, the second type of energy, this is the one that we have discussed earlier. It is called potential energy, and they will mention it as E with a subspace P, like the way it is written here. And that energy is mgh, where mg is the weight, mass times gravity, and height is the height of the object. As the definition says, potential energy is what? Potential energy is the energy of an object has because of its position or location. Position or location. It is a static energy. Like when you talk about kinetic is moving. This is not moving. It is for its position or location. It is at one position or one location. Most potential energy is due to gravity, and there are like they have just given us a formula how we get this potential energy. Work is force times distance. Now if we look at gravity, weight is force, weight is mg, that replaces your force, and distance is the height gives you mgh, where this first part of mg comes from force, and the second part comes from distance. Now this is the second formula that we need for our this lesson. Okay, now they have just given us one example. Example says how much work is done in lifting 1 kg book to the height of 1 meter. Now see, you just use the formula. You just remember this formula that work is mgh. They have given you the mass. Mass is what? 1 kilogram. G, gravity, I know I have been using 9.8 meter per second. And they have given me the height. Height is what? 1 meter. 1 kilogram, gravity 1 meter per second square, height 1 meter. I multiply everything together, it becomes what? 9.8 joules. 9.8 joules. So now this is what we need. Every time they ask you about the potential energy, we need 3 things: mass, Gravity is always 9.8 meter per second square if we are discussing gravity on Earth, all right? And gravity on Moon is 1/6 of 9.8. Whatever is the gravity on Earth, we just divide it by 6 and we get gravity on Moon. And the third thing is height. These are the three things we need. We just multiply them together, and whatever is the answer, we just give it a unit as joules. So whenever you have work or energy, the units will be joules. Okay, now let's check this. Potential energy depends on the initial and the final position, difference in height, and is independent of path. If we disregard any frictional laws, it takes the same amount of work to lift a mass no matter the path. Now they say, like if you look at the diagram, there are three things. There are three things mentioned over there. This is number one, this is number two, and this is number three. They have lifted a mass in three different ways. Now see, the mass remains the same. Mass is m. Gravity remains same. All right. Now, in the first instant, this product goes from here to this place. In second, it goes from here, and in third, it goes from here. Now, one thing you need to check is in all three ways, what is the height? Height always remains the same. You cannot change the height of the table. You can bring that object in any direction. Let's say the object is here, and you bring that object from here to here, but still this height remains the same. Now that is what we need. We need height. So that's what they say. This your potential energy depends on the initial position and the final position. It is independent of path. It doesn't matter. You can just bring from anywhere, but the only thing I need is I am looking for this height. That's what I need. So it doesn't matter whether you're moving your object from which side, which direction you're moving it, which path you are following. What we need is we need the vertical height. We just need vertical height to calculate this potential energy. Okay, now let's check this diagram here. No matter which scale we are using, we are just concerned about the delta H is the same. Now they have used the mass. Now this is 0. They consider this as 0. Now if we look at this one here, if this position is 0, we pick up the object up to this point. Now when I check the height over here, this is the positive height. So we calculate the potential energy as m, g, and h. Height is positive. We are going up. Height is positive. We are going up. So work will be in joules. From this point, if we go down, the height is going down. So it will be mg negative h. So we're just looking at the position, like whether we are picking up the object or we are putting down the object. It depends on us. All right, in both ways the work is done, the energy is consumed. Now another example of potential energy is springs. Compressed or stretched, both have their own potential energy. Now the reason they have their energy is, like if there is a spring that is pressed, it is having energy. Why it is having energy? Because If you put something at the top and release this spring, it will just go up. It will just fly away. They have energy. Or if a spring is stretched and you tie something, some object, and if you release it from here, it will just pull the object upwards. So there is a potential energy in a spring. Same way in a bowstring, there's a potential energy. Those who use bow and arrow, they know how it works over there in those objects. Okay, now the next thing is conservation of energy. Energy can neither be created nor destroyed. Very important thing. It just converts from one form to another. In changing from one form to another, energy is always conserved. Now, this is what they mention. Energy is constant. There is no energy created. It just converts from one form to another form. And that's true. It just converts from one form to another form. So the total energy in one system, if the system is isolated means there is no loss of energy. Now, there is a strange thing, like we have cars right now. In our cars, they are actually trying to isolate the system. How they're trying to isolate? Because, we waste a lot of energy. Waste means we are not using that energy. Like in cars, the fuel is burning. When the fuel burns, we do not consume that energy again. That energy is lost. When the cars get warm or the engine is hot, we do not use that energy. That energy is lost. So now they are trying to preserve those energies. These electric cars today, the way they are having this Tesla and other cars, what these cars are having, they are isolating the system. Like when the car starts or when the car runs, the energy produced by the car, or when we apply brakes, the heat energy used by brakes is actually used to charge the batteries. All right. So they are just trying to convert and reuse the energy from the system itself so that they do not have to refuel the car again or recharge the car. There are a lot of things that can charge your car. Heat energy produced by the engine, produced by the motor, heat energy produced by the brake pedals. Everything can be used to convert it to, again, recharge your batteries, the car batteries. Okay, now they say as energy of one system will be equals to energy of another system, or the system is preserved. So if there is a kinetic energy and potential energy at one instant, and kinetic energy and potential energy at another instant, if we add these two, they should be equal. This is for one, this is for two forms. So this is what they say, that energy, potential energy and kinetic energy of the whole system is constant. It is not changing, and it is universal. It is actually in the universe that the energy is same. It is not changing. Now look at this question here. It says, a 0.10 gram stone is dropped from the height of 10 meters. What will be the kinetic energy and potential energies of the stone? Okay, now if you look at this thing, now if I ask you what will be the potential energy, now every point the energies will change. Every point the energies will change. So just check this here now. At any height, the potential energy is mgh. Now when the height is 10 meters, we have mass, we have gravity, and we have 10 meters. That gives me potential energy. 7 meters, mass, gravity 7. Okay, mass, gravity 3. 0 mass, gravity 0 gives me 0 joule. That is the potential energy. Now, since the total energy of the system is kinetic plus potential, kinetic will be total energy minus potential energy. Now, this is, well, the table that they have generated, all right? Or we can just create our own table. Maybe in next lecture, I'll just create the same table. For 10, 7, 3, and 0, they actually calculated the potential energy. This is what we did in the previous problem. And on the same lines, we have kinetic energy. We calculate these kinetic energy. And when we add these two, 9.8 plus 0 gives me 9.8. 9.8 plus 0 gives me 9.8. 6.9 plus 2.9 gives you 9.8. 2.9 plus 6.9 gives you 9.8. 0 plus 9.8 gives you 9.8. Means the energy remains the same. Energy doesn't change. Whether it is at the top or it is at the bottom, energy remains the same. It is not changing. It is just converting from one form to other. Over here, it was potential, no kinetic. Potential is decreasing, kinetic is increasing. Potential becomes 0, kinetic becomes 9.8. This is the logic of energy. All right, now this is all what we are doing for today. And that is chapter 4.2. And the PowerPoint is actually on your D2L. And I'll be posting some review questions